in a graph, if D dominates N, D is not equal to N. Um, okay, I'll restart then. Module 112 is about immediate dominators. We say that node D immediately dominates another node N if D dominates N, D is not equal to N, and there does not exist M which is different than D and M, such that D dominates M and M dominates N. So then we saw an example of immediate dominators, and then we said that immediate dominance relationship forms a tree. In module 113 is we talk about the definition of a natural loop. We said that the natural loop is made of three things: a header. A header is a node which dominates all the nodes in the loop. There is a back edge from a node to this header. So this is an edge whose destination dominates its source, and the natural loop associated with this back edge is the destination D plus the nodes that can reach N, that is the source, uh, without going through D. So then we looked at the example of a natural loop, identified the headers and the package. Then um, one example we saw that there can be loops and some loops can be nested within others. The nested definition, nested we defined by if nodes associated with one loop are a subset of the nodes associated with the other loop, then the first loop is a subset of the second loop. So we said that if two loops do not have the same header, either they are disjoint or one is entirely contained, that is nested within the other. Then we defined something called inner loops. Inner loops are the ones that contain no other loops. So then we specially talked about loops with the same header, and we saw two cases. One in which there was a edge from the header back to itself, and there was another loop, and another case in which there were two loops which just shared the header. So we say that in these cases it is hard to say which is the inner loop, even if we could say that a smaller loop is the inner loop in the first case. This reasoning is flawed because some analysis might add a basic block and then it starts looking like the other case, and so it does not make sense. So to avoid this problem, the solution is that we combine the loops which have the same header and just treat them as one loop. So then we come on to module 114, in which we talk about identifying natural loops. So, so we follow four steps. The first would be to find the dominator relations in a flow graph. Then we identify the back edges. Then we find the natural loop associated with each back edge, and then we combine the natural loops that share the same header as we reasoned about previously. So to find the dominators, we use a forward data flow analysis. Of domain would be the sets of basic blocks. The transfer function is just a simple transfer function that the out of a basic block is the value at in of the basic block union the basic block itself. The meet operator is a set intersection because the dominator means that it should be present in all the paths. A boundary condition is that out of the entry node is the entry node itself. So an interesting fact about this is that we can compute the fixed point solution of this in a single reverse post order pass. Then we saw an example of a graph in which we saw the reverse post order, and we found the dominators of it. And we said that the intuition behind how we are able to compute this is in a single part is that the all the potentially dominating predecessors are visited before we visit that node. So these can also be identified through a depth first search, which would be the same as the reverse post order. In fact, reverse post order is also called a depth first ordering. So then we discussed the algorithm for depth first search and depth first ordering, in which we give each node a depth first number, and the depth first number indicates the order in which these nodes would be visited to visit them in a reverse post order. So and also we saw that multiple reverse post orders are possible for the same graph. In module 115, we we saw a depth first numbering example, and then we saw that for a particular depth first numbering, there is a retreating edge, which we defined as an edge m to n is a retreating edge if the dfn if the dfn means the depth first number of n of the destination is greater than dfn of m, that is the source, is greater than equal to the dfn of n, which is the destination. So that means that effectively that m was reached through n during dfs traversal, and this is sort of a back edge, not exactly back edge, but yeah. Yeah, so also we recall that back edges are not a property of the DFN, they are a property of the graph. Um, so we also observe that if hmm, that dominator should have a lower DFN than the node it's dominating, because since it's a dominator in every ordering, that node would be visited first. So the DFN of the dominator would be less than or equal to the DFN of the node it's dominating. So then uh, we state a theorem that every back edge is a retreating edge, but not vice versa. The reasoning is that the back edge requires a stronger property that the destination dominates the source, but retreating edge requires a weaker property that destination was registered before the source in that particular depth first ordering. Um, right, so we saw an example in which we found the back edges, and there were two DFN, the two orderings in which we saw that there were some retreating edges which were not the back edges. Right. So then we come to reducible graphs. We say that a control flow graph is reducible if and only if all the retreating edge in any depth first numbering are also back edges. So this effectively means that all cycles in this graph are natural loops. All cycles in reducible graphs are natural loops. So then we define the loop nesting depth of a reducible graph. We say that L1 is less than L2 if loop L1 is less than loop L2 if L1 is nested in L2. So the depth is then we define as the longest chain of such less than relationships in a graph. Right. So then we talk about constructing natural loops, and we say that after we have identified a back edge n to d, we can remove d from the control flow graph and find all nodes that can reach n. N was the destination of n was the source of this back edge in this modified CFG, which is effectively amounts to computing its transitive closure. So we also see that we can convert graphs to reducible graphs, which we can do by duplicating some code, but this may lead to exponential growth in code size. Uh, Module 116 is we talk about the symbolic analysis of loops. So the motivation we saw with that if there is a loop and we want to parallelize it, so how would we go about it? We observe that the given the data flow analyses we have already saw, they don't help. And also, like, also the parallelization is not immediately obvious because there are read after write dependencies. So one variable is getting written in an iteration, and that variable is getting read in the next iteration, so it is not trivially parallelizable. We see that if we apply available expressions to the loop, um, then uh, then the available expressions inside the loop, there are no available expressions inside the loop. So then we say that the better solution would be um, to have the the expressions which are not directly available inside the loop, but which we can infer through some algebraic relations. So like so we say that we can say that the sum, if we observe, then it is at after ith iteration, it is the sum of first I natural numbers. So so that is that. And this say that this requires some loop level, some sophisticated analysis.
So, Arpit,
So
your
yeah.
camera has been covered somehow. I don't know.
Oh, sorry.
Yeah,
Oops.
yeah. Please continue. Yeah, sorry for disturbing.
Um, yeah. So, where- yeah. So we compute the transfer function of a loop iteration FB. So it is basically the transfer function of the body, and it excludes the back edge. So if so we define the transfer function for k iterations as f superscript k b, which we define as the composition of f superscript k minus 1 composed with fb. um, right. So the shape of this transfer function is that it takes an available expressions map and returns a new map. We say that we observe that after one iteration, so the new map would be such that new map is m prime and the old one is m. So we'll have that m prime I is equal to mi plus 1 because we are incrementing I by 1 in the loop body, and m prime sum is m sum plus mi. And so we can compute that using this recurrence relation, we can compute that what would happen in ki iterations. So using symbolic analysis and some algebraic simplification, we can compute that after ki iterations, what would be the expression in sum and I. So so we are able to talk about number of iterations of a loop that are executed because it has a single entry. So we know that this the same node which will be visited again and again. So we can reason about the number of iterations. And we also observe that this analysis is a bit more sophisticated than the DFA, since we are generating expressions that didn't necessarily originally exist in the program. Right. So the final answer that we get that after k iterations, the value in I would be k, and the value of sum would be initial value s plus k into k minus 1 by 2. So then we can do further interpretation that replace k with I. So we'll remove this dependency on number of loop iterations as well. So there is also the concept of loop trip count, which is the number of loop body executions between loop entry and loop exit. So that's the K we have been talking about. So we can also see that the exit condition is that I loop will exit when I is greater than equal to n. So now that we have the expression for I, we can then determine that the loop will exit after exactly n iterations. So, so with all this, we have achieved a more precise DFS solution through a loop level symbolic analysis. So To keep track of k, what we can do is add k equal to 0 for the initialization and add an expression k plus plus at the end of loop body, and then the analysis would also keep track of this loop trip count. And yeah, that's it.
Okay. Thanks, Arpit.